Alright, this is the last video on section 16.7 about surface integrals. And in this video, I'm going to work out more examples of vector surface integrals. And let's remember, given a vector field on R3 f of x, y, z and an oriented surface S, and then vector surface integral, or flux, is denoted by this, but to compute it, basically there are three steps. The first step is to parameterize the given oriented surface by using the parameters uv, r of uv as parametric surface, where x component is a function of u and v, y component is a function of u and v, and z component is a function of u and v. And then step 2 is to compute this cross product and check the orientation, meaning that make sure that the given orientation, namely the orientation of S given in the program, is consistent with this cross product. If this one is the opposite to the given orientation, you have to choose the other way around. You have to multiply -1 to this. So that's step 2. And then step 3, you plug into the formula for this, namely this flux or vector surface integral is computed as dot product of this vector and this vector. Okay, this is calculated in step 2, and this one is obtained by plugging in the parameterization to the given vector field, meaning that you replace x here with xuv, y by yuv, and z by zuv. And you get a function of u and v, and then you take the dot product, and then this dot product gives you a scalar valued function of u and v, and then you just double integrate that scalar valued function over whatever the domain you have for d, for u and v. Okay, so like I said, I'm going to work out more examples in this video. Example number 1. Example. Let our f be, or f of x, y, z be, yi plus y plus z minus 1 j plus x plus z minus 1 k and S is the triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. With outward orientation. Well, maybe upward orientation instead of out. Upward orientation. What is this? Well, so here, let me visualize S. S is a triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1. So it's a triangle like this. And now, what's the equation of this triangle? Because this is your exercise. Equation of this triangle is written as z is equal to 1 minus x minus y. All right. And then upward orientation, so the orientation is in this direction instead of going downward like this. Orientation is upward. Well, if you look at this point, it goes this way. That's the orientation of our S. Okay, then now we want to compute. Okay, then the problem is evaluate this f dot ds So that's the problem. So here's the answer. So like I said, there are 3 steps. Step number 1, parameterize the surface. Well, how? Well, in this case, our surface, which is actually a plane in this case, but in our surface is z is equal to something. And if our surface is given like z is equal to something, something is in terms of x and y, then there's a canonical way of parameterizing it. Namely, we use x and y as parameters. Namely, u is x and v is y. And then x component is just x. X is equal to x, so to speak. And y is y. And the plus z is this. 1 minus x minus y, k. All right. Then, so that's step 1. Step 1 is done, but we have to figure out the domain of the integration, d, at this step. And that is obtained by all the possible regions x and y can move around for this surface. In this case, it's just here. So this is our d. So d is the triangle like this. All the possible regions x and y can move around. So this is 1, 1. And of course, this line is y is equal to 1 minus x. And this is our d. And then strictly speaking, the parameterization transforms this triangle to the given triangle. All right, so that's a parameterization, step 1. Now step 2, compute this one. Compute Rx cross Ry. Well, to do this, first we compute Rx, and that is, you just differentiate this with x, you get I plus 0j minus k. And then if you differentiate with y, you get 0i plus 1j minus k. Because if you differentiate with y, each of those terms, you get this. And then from this, from those, you can compute the cross product ijk, and then 1, 0, negative 1, 0, 1, negative 1. And that is equal to, well, it turns out that it's 1, 1, 1. Okay. Then now, once we get this, we need to check the orientation. Well, vector 1, 1, 1 has positive components for all x, y, z. So indeed, for this, you will actually see that vector is going like this, 1, 1, 1. But typical way, canonical way of checking this is to look at a one test point, but 1, 1, 1 is independent of the choice of the test point. So no matter where you are on the triangle, the vector representing the orientation is 1, 1, 1. So it's like going this. The vector 1, 1, 1 is vector like this way. 1, 1, 1. And then this is upward orientation, so to speak. So we can use, so therefore we can use, we can use this one. Okay, if the problem were like downward orientation instead of the upward orientation, then in that case, you'd have to use the other way around. In which case, this would be negative 1, 1, 1. But for this, we could use this. So this orientation is consistent with the given orientation. So that's step 2. And step 3, just plug into the formula. Plug into the formula, meaning that just compute this. Yes. And that is df of r of x plus r of y dot x y and dx dy. What's this? This one is you plug in the parameterization to the vector field you integrate. What is that? Well, in this case, the vector field you integrate is this. Let me just copy it. So here, f x y z in this example is yi plus y plus z minus 1 j plus x plus z minus 1 k. I just copied it. And then we know that our parameterization is xi plus yj plus 1 minus x minus y k. And then what you have to do is just to plug this into here. But what does that mean? That means from this you get f of r of xy is f of x is x, y is y, and z is just a z here, z component here. That means this. Namely, in other words, you just plug in those to here. So for this expression, y just stays as y, and then z is 1 minus x minus y minus 1 j, and then plus x stays x, 1 minus x minus y minus 1 k. All right, and then if you simplify this, you get yi. Actually, a lot of cancellations, and you get negative x j. And here also a lot of cancellations, and you get negative y k. Okay, so that, I'm sorry. Sorry, this is a typo. X, y, sorry about that. So this is here. And we already know that this one is 1, 1, 1. So by using bracket notation, this is, by the way, y, negative x, negative y. So therefore, the answer is you double integrate d of this one minus x minus y dot 1, 1, 1 dx dy. And that is equal to double integral d, and then y. So you just take the dot product, and since this is just 1, 1, 1 minus x minus y dx dy, and that is equal to negative x dx dy. Then now, what's d? D was, remember d is equal to the triangle, like this. So this is just a double integral of the triangle like this. Here is it. So let's remember how to double integrate. You fix one of the variables and integrate with the other variables first. And then in this case, it doesn't matter which one because it's symmetric, but let's just fix x. So each fixed x, your y value varies from 0 to 1 minus x. So this is written as, so you first integrate with y, and y is from 0 to 1 minus x, negative x, dy. And then you integrate with x, and x is from 0 to 1. And so therefore this is from 0, 1, negative xy, and y is from 0 to y is 1 minus x dx, and that is equal to 0, 1, negative x, 1 minus x, and y is 0, so it's 0. So that's it. Well, maybe, to be more precise, this is negative x times 0. That's 0. And then this is, if you simplify this, you will see this is just x squared minus x dx. And then if you work this out, you are supposed to get 1, 6. All right, so that's the answer. All right. One more problem. Here's an example. So evaluate the vector surface integral f dot ds with our vector field f, or f of xy, yz squared I plus x squared yj plus z squared k, and our surface S is the disk with radius 1 and the center 0, 0, 1 with a upward orientation. Okay, so that means pictorially, what is this? So this is a disk with radius 1, meaning the circle or disk with radius 1, with center 0, 0, 1. It's not 0, 0, 0, 0, 0, 1, meaning that x is 1, x is 0, y is 0, but z is 1. So that means this is basically a disk with radius 1 floating in the air at height z is equal to height 1. So it looks like this. X, Y, Z. The disk floating in the air with center 0, 0, 1. So it's like this. So this point is 0, 0, 1. And the upward orientation, the orientation of this disk is going upward. So upward orientation like this. Remember, strictly speaking, orientation is consistent choice of normal vectors. But anyhow, let's just do this. So the procedure is always the same. Remember step 1, what you have to do is to parameterize the surface S. Okay, now how? Well, actually, surface in this case is the disk with radius 1 at center 001, like floating in the air, but that means this disk is on the plane. This disk is actually on the plane z is equal to 1. Okay, so that means after all, our surface S is just z is equal to 1. S is actually the plane. Z is equal to 1. Then now, remember, whenever your surface is given like z is equal to something, the way to parameterize is x is u, y is v, so to speak. So that means we could use x and y as our parameters, namely x, u is x, v is y. So this is xi plus yj, and then plus z, but what's z? Well, z is 1, so we have just 1k, that means just k. So that's a parameterization. Then now, what's the domain for x and y? Well, x and y moves around the region, disk with radius 1. So in this case, xy just moves around the disk with radius 1. And then by r, this gets mapped to the disk floating in the air, like in the picture like this. Okay. So this is our D. So that's step number 1. Now step 2, compute Rx cross Ry. What's this? In this case, when you do this, once you get used to it, you can just do it like this. ijk, put ijk. Then now, for the second row, what you have to list is the derivatives of those with respect to x. So that means you differentiate each of those by x. If you differentiate x with x, you get 1. If you differentiate y with x, you get 0. And if you differentiate 1 with x, you get 0. And similarly, the third row here is a derivative of those guys with respect to y. So that means if you differentiate x with y, you get 0. If you differentiate y with y, you get 1. And if you differentiate 1 with y, you get 0. Okay. And then if you work this out, you will get k, vector k, or this is the same as 0, 0, 1. Then 0, 0, 1, the vector 0, 0, 1 is a vector pointing upward. Right? K is vector like this. So that means everywhere on this disk actually, vector is pointing upward. K. All right, so that means this is the upward orientation. This implies that the orientation given by this is upward orientation. And so therefore, that's the right orientation, namely that's the orientation given in the problem, upward orientation. Okay, so that's a correct orientation, meaning that it's a correct orientation. This is correct. All right, so that's step 2. Now step 3. Just plug in everything to the formula. Meaning that the given surface integral is computed as double integral over d, where remember d is just a discrete radius one, f of r of xy dot dx dy. And remember what f was? Let me recall. Our f was, what was our f? F is this. It's given in the program, this. By using bracket notation, this is yz squared, xy squared, and z squared. And we already computed r, or r of xy, as xy1. That's this here. Where is it? Where is it? Here. Okay. So, from this, what do we see? This is, what is this? You plug in r to f, meaning that you plug in this to here, namely x is x, y is y, and z becomes 1. So therefore, if you plug in, what you get is y times 1 squared xy squared. So x is x, y is y, and z is 1. 1 squared dot this 0, 0, 1, because this was this and that's this. Dx dy. And that is equal to, fortunately, 0, 0. So it's just 1. Dx dy. It's 1. If you compute this dot product, this becomes just 1. Okay, so therefore this is double integral of constant function 1. That means that's the area of D. Remember, if you double integrate constant function 1, what you get is the area of D. And then in this case, D is just discrete radius 1. So this is just a pi. Or if you like, you may directly calculate this double integral by using polar coordinates, whichever you like. Anyway, so that's pretty much it. And yes, so this is the end of the video.